Okay, I will start us, I think. Good evening, everybody. Welcome and thank you for joining us this evening. First of all, let me introduce myself. My name's Abby. I work with Barry Cranford, who's the founder of the London Java community, and I have the privilege of hosting this evening's meeting. For those of you who don't know, the LJC is one of many communities that RecWorks run. RecWorks are a tech recruitment company with a massive difference. As a company, we believe that recruitment can be a force for good in the industry beyond just placing people in jobs. We have a particular focus on learning, mentoring, and personal development. From our perspective, if people want to learn and other people want to teach or share knowledge, we're more than happy to connect you through our communities and events like this one tonight. We see this as giving back to people we've worked with in the past, but also paying it forward to those we hope to work with in the future. We have run so far over 700 events for engineers and developers within the LJC, students, graduates, CTOs. We have run conferences, lightning talks, hackathons, all sorts of different events. We've also made over 3,000 introductions so far between our mentors and mentees in our Meet a Mentor program. And we love to give opportunities to speakers like Aslan tonight, who's speaking to us. If you'd like to know more about any of our communities, please do get in touch with myself or Barry or Helen, and we can take it from there. But with no further ado, I'm going to hand over to Aslan, and he can introduce himself and give us his presentation for this evening. Go for it.
Thank you, Abby. Thank you everyone for joining this session together with this evening. Yeah, actually I will be, my name is Alparslan. You can call me Aslan. Actually, it is easier to spell. I'm working for Hazelcast for nearly 7 years, and today I will be presenting you about distributed transactions in a service mesh. Let me share my screen, and I will also give a bit more details about myself in the presentation. Yeah, I think you can see it right now. Okay, so yes, as I mentioned, I'm a software developer at Hazelcast for nearly 7 years, and I'm mostly dealing with the cloud native issues of Hazelcast platform. Our team is also currently implementing a new project which we called Hazelcast Platform Operator for Kubernetes. So it will help us to install Hazelcast platform on Kubernetes in a very easy way, in a very user-friendly way. Other than that, of course, I love to solve problems if I can. And you can always reach me using my email, alparslan@hazelcast.com. So yeah, let's start. First, before our discussion, let's start imagining. Let's imagine that we are working for a. Firstly, let's imagine about the business itself. It's a large e-commerce business. This one, you can think that there are more than thousands of transactions per day, and there are multiple and variety of goods are sold throughout all the day. Actually, there are multiple locations that people are buying our products, and there are multiple time zones. So it is really a large one. And also, you are a developer in this company. You started working as a developer. The company has nearly hundreds of IT workers. Again, there are multiple specialized teams, and these teams are responsible for different features of the our development environment, our application backend or front end. And also they are also placed in different locations around the world, so they are working remotely. So within the kind of this company, your CTO comes to you one day and asks this question: if you would like to set up our software environment, the whole software from scratch, which architecture will you choose? He asked us, and most likely, since this is a large enterprise company, dealing with multiple different features in the same software environment, and also there are multiple different teams, it will be much easier to use microservices instead of monolith, right? Yeah, you can also choose to run monoliths, with a monolith application, but there will be lots of problems, which will come in the second slide. If you were a smaller company, if you have a really small application base, then yeah, it might be easier to choose. It might be better to use monolith than the microservice architecture. But we are mentioning about the enterprise application. So what are the problems with these monolith applications? Firstly, they are too large and complex. They are too large and complex because they had multiple features implemented to provide to serve to the customers or the users. So this makes them complex, and also most likely they are communicating to, or they are touching to different multiple endpoints, maybe system of records. So it makes them complex. Since they are large and complex, we can directly say that they are really difficult to maintain, right? Because right now you need to change a small piece of code, but you need to think all of the application together. So it's very difficult to maintain them. Also, one of the problems is they are very difficult to scale, especially when you think of horizontal scaling. It's very difficult because most likely your application is not idempotent. The endpoints cannot get requests from different endpoints and just run them like a microservice. So it will be very difficult to scale horizontally. You need to scale the application vertically, which means that you need to increase the hardware power, which will be really costly and also difficult, because the hardware has limitations. If you have just increasing the power in just one box or one server backend, so it will be difficult to scale. Also, you have a slow startup time. This will be again the problem with the with restarts of your application. Of course know that if you're a software developer or if you're a DevOps engineer, you know that startup times, you eventually restart your application, and this application restarts, if they are slow, then you will need more time to cover, more idle time to cover. So it will be a bad thing for your application if you have a slow startup time. And also this is directly related with the updates. If you are using monolith application, monolith architecture, then you need to redeploy the whole application at once when you are updating the application. Again, this will cause maintenance issues, especially when you think of maintenance windows. It will be really difficult. Since we are talking about e-commerce business, each second or each minute will cost you lots of money if you cannot serve your customers. So this will be also a really big problem. And so on. Actually, there are many other problems with monolith applications if you are a large enterprise company. Of course, as I said in the beginning, if you are a small business, if you have just a small application, then it won't mean anything to run microservices because of the reasons that we will mention in a minute. So you choose microservice architecture, but your story didn't end up there. Actually, on the contrary, it just began, because now you need to deal with multiple issues within your environment. Sorry. Yep. This picture is just a drawing, actually, just the imaginary drawing of the microservice environment. But you can see that there are multiple backend services that they are communicating. They're dealing with multiple system of records, most likely databases, maybe some web services. There are multiple front-end services to serving the users the front-end of your applications. And also there might be some message brokers, Kafka or something like that, to handle the communication and the service intra-service communication. And you most likely these services have not just one nodes. They will most likely have multiple instances of these services to scale them up. So there will be a complex environment to maintain. It will be you will need multiple tools and teams to maintain your environment, application environment. So when we talk about microservices, the microservices best run in containers in our days, actually, because when you run in a container, then you can isolate the environments from other applications, so it will be much easier to handle and maintain your application. And when we think about containerization, these two tools are the most common ones that most likely you heard them lots of times. First one is Docker, the containerization tool itself, and the Kubernetes, the container orchestration tool. So in an environment, in an enterprise company that we imagined, you should be definitely having some kind of container orchestration and container engine to run your microservices. But as the number of your microservices increase, which will definitely increase in time, because the requirements will, the business requirements, the internal development team requirements will increase in time, and you will most likely increase your number of microservices, and you will need new tools to handle and to maintain your environment. I can give an example for this one, actually. I know that a real company, actually, that has more than 250 microservices running just in one Kubernetes cluster, and they have more than thousands of nodes running, actually pods running in the same environment, Kubernetes environments. So you need some new tools to observe the microservices, to handle the traffic, to provide security, to handle the to see the logs and everything, actually. So with this part, actually, the service meshes come into the point. So what's the service mesh? Yeah, a service mesh is actually an infrastructure layer application. It's running in the infrastructure layer. So it means that you are dealing the applications intra-communication, and it enables the secure source communication. You install the service mesh into your Kubernetes environment, and it handovers the communication, in intra-service communication, east to west communication in the Kubernetes environment, and it actually provides some features. There are three main features that a service mesh provides. The first one is the traffic policies. You will have the control of traffic policies, since you handed over the whole communication to the service mesh, and there will be an out-of-box security. The communication will be secured. most likely you'll have SSL TLS communication between the services out of the box. You won't need to, the developers won't need to handle these issues, and also the observability, since you will handle the service mesh takes care of the communication, then it will actually see you can have a bigger picture of your application background, application environment. You can have some visualization tools, or you can also have some kind of debugging, logging, or traceability the tools that you get with a service mesh. In this picture, actually, you can see a summary of the architecture of a service mesh, how it is structured. I will come to the detail when we are talking about the specific service mesh, which will be Istio. But in here summary, you can see that there's a control plane. A control plane, and this control plane communicates with services. This part in the plane that we had services is called data plane. This data in each service, you can see that there's a sidecar. This sidecar belongs to the service mesh. In each pod, there's the original application container and also the sidecar container, and the whole communication between the services are done through the sidecars. So there will be no service-to-service communication, a direct service-to-service communication. Instead, the services will communicate to sidecar proxies, and these proxies will communicate to each other in the control plane to provide these features. We will come to the detail. There can be also, of course, an ingress and egress output, egress features. This can be provided with the service mesh. The main service mesh products in today actually are right now the most popular one is Istio, which is developed by Lyft, and it is using Envoy as the proxy, and it's the most popular one right now. There are some criticisms about Istio, but yeah, it is we can say nearly the most mature one. Also, there's a HashiCorp's console as a service mesh, and we have Linkerd. Linkerd is the first featured service mesh. When the service mesh is keyword, the featured keyword is first used with Linkerd. Right now, they have developed recently. They have developed Linkerd 2.0, which is developed they developed from scratch, and it is. We can say that based on the articles that I read, I haven't directly have a benchmark comparison between Linkerd and Istio, but the articles are saying that Linkerd is much more performant than Istio. But I think they are both not that much mature to provide a good information about production environments. So there are also some other service meshes, such as App Mesh, Kuma, and Open Source Mesh, which Open Source Mesh is the standard of the cloud native foundation. So there are more than these products in the service mesh world. So this picture also is a good one to understand when we need to use a service mesh in our application environment. So by the way, I got this picture from the Nginx blogs. So it's really a good one to see how the relations between cost to complexity of the service mesh and the other native Kubernetes proven services. So imagine that you have the simple application here. You can see that the axis actually says the number of applications, number of microservices in your environment. So if you have just a few applications, you won't need any microservice meshes in your Kubernetes environment, because most likely the native Kubernetes services will help you to maintain your environment. But as you go, as the number of service meshes increase, at some point, the service meshes will provide a better cost to when we compare to the native Kubernetes. So you can see that the service mesh has a nearly constant cost at all levels. But we can also think that as it is mentioned here, as service meshes mature, because they are not mature enough, as I mentioned before, their cost will go down also. We expect them their cost to go down. So it will be much feasible to use a service mesh in a smaller application environment. So we installed service mesh, and we are trying to solve some issues in our application environment, but there are still more problems that we need to solve. This one actually comes with about the transactions. So you have multiple services, you have multiple system of records, databases, the places that you need to write, persist your data. And also you will need some transactional operations. Sorry. Most likely, for instance, when you are purchasing, when a customer is purchasing a good from your e-commerce application, they might need to update in your application, and your application might need to update your product database, and also the banking service database, and also more likely the user database too. So you need to do all them on transactional way. So prepare yourself to meet the distributed transactions, because you are all right now running in a distributed environment. The basic problem that we have to talk is the dual write problem. The dual write problem is this diagram shows a very basic service for our e-commerce system. Imagine that you have the front-end service that provides the user interface to the user, to end user. And also imagine that this user is trying to purchase a good from our e-commerce website. So this front-end service need to contact the user service, product service, and banking service to update all of these databases, the user database, the product database, and also the banking database. Most likely the banking service and the banking database will be placed in another way. So this will be also another issue. So what happens if we had an issue with the banking service? If we had an issue with the banking service, then all of our updates needs to be rolled back, right? The product service needs to roll back the update in the product DB, and also user service also need to roll back the update on the user DB. So we can say that all of these operations needs to be in the same transaction boundary. They need to be run at once, and if any of them gives an error, then we need to cancel, we need to roll back all of the operations that are executed. So this is the dual write problem. So let's show how the dual write problem works. Yeah. Firstly, let me arrange my here. So I have an environment in the clear this one part. Yeah, I have an environment, Kubernetes environment running in the GKE, Google Kubernetes engine. I can show you the services, and yeah, in the default namespace, there's only one, the default Kubernetes service. And also if I check the pods, there's no pods in the default namespace. Okay, so is a clean one. Just we had what we have is the in the backend Istio service mesh is installed and it is running. We can check it is services in the namespace Istio system. Yeah, you can see that there are multiple services it's running in this namespace. They all belong to the Istio control plane. So the Grafana, egress gateway, ingress gateway, Istio D, and Jagger, Kelly, Prometheus, tracing, and Zipkin. So yeah, it is installed and the Istio is installed. What we will have is actually we have an application. We have the same application that we mentioned here. We will have the front-end service, the user service, the product service, and banking service. Let me also show you the just a minute. Sorry. Yeah, let's see this deployment file that we'll use to deploy our application on Kubernetes. There's a user service. We will install just one replica in just one pod. There's a user service which is a cluster IP type of service, and product service as same as the user service, and banking service, and lastly the e-commerce service. The e-commerce service is all know about user service, product service, and banking service. And it has a load balancer type of service that the user can communicate through e-commerce service. So let's deploy our application deployment file and see services. I think you can see the output. Let's see the services created. Yeah, we have 4 additional services: banking service, e-commerce, product, and user service. And for the e-commerce service, we have a pending external IP. We will get it in a few minutes. While we are waiting for that one, I will also like to show you about the visual representation of these services. This is Kiali, which is a tool provided with Istio. You can visually see your services, your applications in your environment. There are also some other features that you can use, but we will just use this graph feature to see our services. So let's check again. Yeah, we had the external IP. So let's access to our application using this external IP and see what we get from the application itself. Okay. Yeah, this is our application. You can see that this is a really basic e-commerce application. We have a single product. It's a smartphone, and it costs £4,500. You can see the product stock here, 10, and also we will see you can see that there's a available user credits here, which is £10,000. This one you can think that's user credits. The user already applied some vouchers and get this amount of credit in their user data or in their account. So as I mentioned, we have, you can see that we have 2 different services. The user service provides this information, the user credit information, and the product service provides these information, the details about the product, stock, the price of the phone, and everything. So let's add our product to basket, and let's go to the checkout page. In this checkout page, we have 3 fields to fill. First one will be the quantity. The second one from the amount from your credit, how much we will deduct from our credits when we are purchasing this phone. And this will be the amount from your bank account. So this will be taken from your bank account. And so you can easily guess that this will be, when we are buying the service, the front-end service will try to communicate to banking service to get this amount deducted from your bank account. So let's think that this will be, we will have 3 funds, and we would like to get, for instance, 3,000 of our 3,000 pounds from our available credits. So what you expect, if everything goes okay, there won't be any problem. But our application actually will get an error from the banking service. So when we click on the buy now button, we will get an error because the banking service will throw an internal server error. So what you expect? There shouldn't be anything, right? There shouldn't be any change on the quantity, the product stock, and there shouldn't be any change on the amount of our credits because we couldn't complete the transaction. But when we click on this one, yeah, we got the internal server error. And when we go to the front page, you can see that the product stock is now 7 and available user credits is now 7,000. It means that we had a dual write problem here. We had the exception from the banking service, but we couldn't roll back the updates on the user service and also on the product service. Also, we can also check this one. Yeah, here we tried to communicate the banking service, but it didn't work. So we had the dual write problem. This is the basic demonstration of the problem. So let's continue with the solution. So what we need is to provide distributed transactions because we have a distributed environment for our microservices. There are two main types of distributed transactions. There are more than these two, but two methodologies are the most common ones. First one is the two-phase commit, which is also known as 2PC, and the second one will be the distributed sagas. The two-phase commit is the one with the strong consistency, but it has some drawbacks. We will talk about them. So how it works is that front-end service communicates when the front-end service gets the request from the user, it communicates to a coordinator, a 2PC coordinator. This coordinator actually, as this is from the name, you can understand from name, it coordinates the whole transaction. And there are two phases in this transaction. The first phase is the prepare phase. On the prepare phase, the coordinator will ask all of the services to prepare their transactions. And if all of them say, okay, we are ready to commit, then coordinator says that, yes, this is the second phase, commit your transactions. And then they all commit their the operations, and then we will get a transactional way. If in the prepare phase, we had an issue with any of the users, any of the services, then the coordinator sends a rollback message to the services, and the services won't commit their changes to their databases. So this works as like this in basic ways. And as I mentioned, when we have an issue with the banking service, we will have the rollback for the other services. Yeah, when we come to the pros and cons of the two-phase commit, the advantage of 2PC is you will get the strong data consistency, which is a really good thing, especially if you are running if you need to run a reliable operation. And also you will get the read-write isolation, which means that when you are running the operation, the other request will see the old values, not the intermediate values. You won't have a stale data read on when you are running your transaction. But when we talk about the cons, actually, the most important one is the two-phase commit is a blocking method. So when you start the two-phase commit, it blocks all of the other requests because it needs to complete the operation. And when you talk about blocking operations in a distributed environment, then you will get some issues because on distributed environments, you will have the network latencies, which is the most important latency. When you wait for other sources to complete for some operations to complete, then you will have really slow performance. And also, this two-phase commit also needs XA compatible data sources. So your data sources need to be also compatible with the XA standards. You will get also some scalability issues and coordinator failure problems because the coordinator will be the single point of failure at this part. There are some solutions to prevent these issues, but yeah, again, this is not the one if you would like to have availability over consistency. Our second approach is the distributed Saga approach. This one is actually a more available, less consistent version of the distributed transactions. So in this part, you can see that there is not a single coordinator that coordinates the whole transaction. Instead, all services are responsible for their own transaction. The front-end service again asks directly to the services, and these services try to run their actions. If they had any issues, then they will call the other products or other services compensation actions. The red dotted lines are the compensation action calls. For instance, if we had an issue with the banking service, then the banking service should call the compensation actions of the product service and user service. What is the compensation call? Actually, it is semantically endorsed action. It is a kind of canceling action for the actual action. But of course, this is not something like a regular rollback in a RDBMS. Actually, you need to provide the implementation of the compensation action. You can think that, for instance, as the regular action, if the regular action is something like inserting a data to your inserting a row to your database table, then the compensation action will be deleting of that line, that row, or somehow putting a flag that makes that row obsolete. So we will also come this one. This is the weak point of the distributed sagas, because we need to implement these compensation actions. This picture also is a good representation of a distributed saga. It is easier to understand from this one because the actions are in order here. So imagine that you are booking a trip on a website. So for booking a trip, you need to first plan the meeting. If the plan meeting is completed successfully, then you book the flights. If it is successful, then you book the hotel. Again, if it is successful, then you book the transport. If at any point, for instance, let's imagine that book hotel, you couldn't book the hotel. There's an exception. There's an error from hotel booking service. Then you call to cancel the compensation action for this one. Also, you need to call compensation action for book flights operation and also for the plan meeting operation. So you all cancel backwards. You can say that. There are multiple methodologies that you can implement a distributed saga. The main two ones are the orchestration and choreography approaches. In the orchestration approach, mostly one of the services are responsible for running the whole transaction and calling the compensation actions if there are any errors. In the choreography approach, actually, all of the services are responsible from their own running, and most likely they are communicating. The services are communicating through a service. It might be an event sourcing service or something like that, but all of them will be responsible from their own running and compensation action calls. So when we come to the advantages and disadvantages of the distributed sagas, The positive side will be of course, it will be running asynchronous because all of the services are, sorry, all of the services are running their own transaction, and they can run asynchronously without blocking each other. And also another good benefit is you can run this, you can run your Sagas in heterogeneous distributed components. For instance, you can have a Node.js service, a Java service together. You can have different databases or different web services that you need to call. All can work together within a distributed Saga. And also, of course, you don't need for X8 transactions, as you mentioned in the 2PC. And surely this is scalable, horizontal scalable, because all of them, again, all the services are responsible for their own transaction. The disadvantages is it has the eventual consistency. This is not a strongly consistent method to run the transactions. And together with the eventual consistency, there is no read isolation. When when you are running a transaction, if any of the servers persisted their value, since they are asynchronously running, all of the servers are asynchronously running. If you would like to reach the previous, and if you would like to reach the values that is changed, then you will get the updated value. You saw there might be a stale data read on your calls. Also, one of the big problems is the compensation function development. You need to find a way of semantically reversing your action, your function, and it will be costly because you will need additional implementation time and workforce. Also, you should consider about compensation failures. You need to find a way to how you can handle the compensation failures. So let's talk about our solution that I will propose. Before talking about the solution, I need to first say that this solution is not a production-ready solution. I'm talking about this solution to show you an example of distributed Saga implementation, and also what we can achieve with the service meshes, what they provide us, and also what are the problems with these approaches. So as I said, be careful about it. This is not a production-ready solution. And also, I will call our solution Propeller, which we call it internally, actually, when we are talking with our colleagues. If I say Propeller, then you can understand that it is about our solution. So let's talk first about Istio's architecture deeply. This is a similar diagram that we talked in in previous slides. So the mesh in Istio mesh, in this Istio service mesh, there's a control plane, and this control plane contains multiple microservices. Actually, Istio, the pilot, Stadel, and Gale, and these control plane services provide features to the data plane by getting the information from them through the proxies. The proxies here are the Envoy proxies. They are called Istio proxy, but actually they are based on Envoy. So we can say the Envoy proxies. And each of these gray squares are the pods in the mesh. And you can see that the proxy and the service container are running in the same pod. It means that the proxy is running as a sidecar. So the service is communicating through the proxy itself. And again, as I mentioned in the previous slide, there is no direct communication between the services. So service A doesn't call service B directly. Instead, it is calling this proxy, and then through this proxy, the service mesh traffic is provided actually in between the proxies. So this is the base. This is the main architecture of the Istio, and you can see that there can be an egress traffic and also egress traffic using these, again, proxies. Another feature that we need to talk about is the Envoy proxy filter chain. This is a really good feature of Envoy. that will allow you to enrich or block the communication between the services. So in a envoy proxy, this is the proxy listener and this is the service. There's a chain of filters. These filters can be HTTP filters, TCP filters, or some other security filters, and you can add as many filters as you want. And you can use these filters to, as I mentioned, you can enrich the data while within the connection, or you can cut the circuits, or you can get some information for observability, to get more to trace your communication and so on. So this is a really good one, and we will use it in our solution. And this diagram shows us the basic representation of our solution, propeller solution. So again, we will have the user service, product service, and banking service. And as you can see here, these are running the services as the main containers in these pods. And we are also running the proxies for which are installed by the Istio. So in this proxies, we will add a filter, which we will call propeller filter. And this filter, it will be added to the filter chain of these proxies. What we will use this profile filter, we will go into detail when we see the implementation, but these filters will provide information about the transaction to the propeller app, which will be again another microservice running in the same environment. So if we had an issue in any service, then we will get the information from the propeller app, the transaction information, which is stored in a Hazelcast cluster, Hazelcast platform cluster. So we will get this information, and then we will call the compensation actions of the related services in the transaction. So let's see how it works. Firstly, I would like to show you the containers within a service. So let's see the pods that we have currently. The banking service, let's choose banking service. If we check, it is details. Yeah, here, let's see the containers. Yes, the first one is the banking service container, and the second one is the Istio proxy container. So we can say that there are two containers, and also in the list, you will see here that there are two ready containers of the two total containers. So about our application solution, actually, we will install the Hazelcast cluster first, and using this deployment file, deployment YAML file, there will be 3 Hazelcast cluster members, Hazelcast instances, and there will be a service to access these Hazelcast members. Also about our application, propeller application, again, there will be 3 replicas. This propeller application is just a web service. We will see the logs. And again, to reach these pods, these service applications, we will have a service, propeller app service. So we'll use this one. So let's first deploy the Kubernetes, sorry, not this folder. Here, let's our Hazelcast cluster. Yep, the Hazelcast cluster is being deployed, and let's also deploy our application. Yep, let's check the pods right now. Yep, you can see that there are 3 more pods added for Hazelcast cluster, and okay, and we have 3 more pods for the propeller application itself. So let's also check the services. yep, we have the Hazelcast cluster service and also propeller application service. We can also check the KLE console to see this. Yep, the cluster is here and the propeller application is also here. So what we will do is actually, we will, as I mentioned in the slides, we will add a envoy filter to our pods, to our sidecars. Let's do it first, and then we will see what it has, how is the implementation. So we will apply this propeller filter. Yeah, we got the propeller filter created. Let's also check envoy filters. So yeah, this is our filter. So what we have in the filter is actually here. This is a envoy filter kind. This is provided with Istio. And you can see that it's an HTTP filter. So it will apply it at the HTTP layer. And it will be operated on insert before. So we will get information before running the action itself. This is a Lua filter. So you can have multiple options to implement your filters in Envoy. Lua is one of them. We used Lua. Actually, there you can also use WebAssembly or C++ to implement your Envoy filters. What we do in this filter, there are two functions. The first one is the envoy request function, which will be called when the request comes to the proxy. What we do here is actually we just get the information about the transaction. So we are checking for the transaction ID, and we are sending this information to our propeller application. You can see that here we are sending this information to our propeller application. And the second function is the envoy on response, which is called on the responses. In here, you can see that if the response status is different than 200, which means that it is not successful in any way, then we call the compensation actions. So to call the compensation actions, first we go to the propeller app to see, to get the compensation action details for this transaction. And then when we get this one, actually, we call all the compensation actions here. We are just calling the compensation actions. So it works like this. And let's try with our application. So in our application, you most likely notice that we haven't redeployed our application. We just applied the filters. So you don't need to change your applications. But of course, our applications already implemented with the compensation actions and their endpoints. I already implemented it and then deployed it. So let's do our operation again and see if there will be any change or not. So let's again try to buy 3 phones, and let's try to take 3,000 from our user credit. So if our solution doesn't work, we will have the available user credits as 4,000, because this amount should be dropped from the user credits, and the quantity will be 4 because we have already 7, and the quantity will be 4 if our solution doesn't work. But if our solution works, then we will see the available user credits again 7,000, and the quantity shouldn't be changed and kept as 7. Let's run it and see if it works. Yeah, we got the error from the banking service, and when we go to our homepage, you can see that the product stock is again 7, and the available user credits is 7,000. So our user service and product service compensation actions are called, and they roll back their operations. And we can also see in our KLE display. Let's make it a bit. Let's make it zoom out. Let's wait a few minutes, seconds to update, because we will see the banking service. Yeah, we will. Let's come here later on because it is not up to date yet. So to see how it happens, yeah, our banking service application gave a HTTP 500 response to our call, and it's intercepted by the propeller filter. The propeller filter checked, since it is the HTTP 500 response, it gets the information about the transaction from propeller app, which check the Hazelcast cluster. And then with these information, the compensation action details, the parameter details, the endpoint details, our filter called the compensation action of both product service and user service applications. And then so we had the rollback transaction. So let's also check KL again. Yes, the KL is updated. So you can see that the e-commerce service called banking service and the banking service called propeller app, get the information from there, and then call the compensation action of user service, product service, and its own compensation action too also. Yeah. So what next actually? Our solution works, but as I mentioned, this solution is not ready for production. But we showed that there are really good opportunities to run with the service meshes, and also it is really easy to implement a distributed Saga in our environment. What's more is that in Hazelcast, actually, we are now implementing a new product, which is called, which we called internally Turbine, Hazelcast Turbine. Actually, it is running in the application layer, not in the infrastructure layer as the service meshes, and it doesn't require a service mesh to run. It's an application toolkit that that provides the distributed Saga transaction features and also service discovery and some more features. So by using this Hazelcast Turbine, you will be easily implementing the distributed Saga transactions by the use of Hazelcast platform cluster. It's not production ready yet, but I think the generally available release will be available in a few months. When it is ready, I will be happy to also do a showcase with that one. Yeah, I think that's pretty much all for the presentation. If you have any questions, we can get it. Yeah.
We have had a couple of questions in the chat.
Yep.
Let me just grab them again. So is the model you've just been telling us about a monolith model or a microservice model?
Mm-hmm. So sorry,
that was the question. Sorry, is it a monolith or microservices?
Microservices, yeah, because there are multiple services that we have installed. Microservices actually there. All of them are responsible from different parts of the application. For the users, handling the users, there's a user service. For the product details, we use the product service, and for the communicating through the bank transactions, we use the banking service. So it's a microservice.
Lovely, thank you. The other question I've noticed on there is, I've been asked it, will you define what sagas are?
Yeah, actually the sagas I mentioned in the slides, but if we can just give a quick summary, the sagas are actually available, more available, less consistent version of the methodology implementation of the distributed transactions. The basic definition will be actually you will use the compensation actions for rollbacks, rollback of the operations, and also all of the services are responsible for their own actions. So this is not a centralized way of running the transactions, I can say.
Okay, great, thank you. Are there any more questions that anyone would like to ask before we close this evening?
Sorry, I'm not using chat, so I have a question.
Sure.
So what happens? Say, so what I understood is the compensation action is triggered by the pod, is the banking application pod, right? Now, what happens? Say due to some error, the banking application pod itself is unable to start.
Yes, actually, that's the flow of that solution that I provided. A good question, because right now, as I mentioned, the solution is not production ready because that's one of the main flaws. Right now, if the error giving pod totally goes down, then you cannot call the other compensation actions, of course. So you need to find out how you can provide a solution with the compensation failures itself. Actually, that's the one of the things that you need to consider about when you are implementing distributed sagas. So with the turbine, I can say that with what we implement within Hazelcast, these problems won't exist because they will be all running in the application level, and Hazelcast itself always already an HA application, so there won't be any problems with these kind of problems. But this one, in this implementation, the solution that I provided, it is not provided, actually, I can say.
Okay, then no problem. Thank you for that.
Yeah.
Great question, Saurav. Thank you.
Yeah, exactly.
Yeah, it's always good to know these things, isn't it? I have just had another question pop up as well. Let me just double check my chat because that's where they all are. Asking, what is Turbine?
Yeah, Turbine is actually, we call the project internally as Turbine. It is not the public name, by the way. It's just the internal code name for the project right now. It is an application toolkit that we can say that provides service discovery, distributed transactions, and also some observability to your microservices applications, microservice environment, actually. So by using Turbine, you will be able to implement the distributed sagas very easily. It will be using the orchestrator pattern, by the way. And also you will have the service discovery without using any service mesh. And also you can have some observability features too.
Okay, thank you. Any other burning questions before I bring us to a close this evening?
Thank you. The Said Yamur, I think, right?
Yeah, thank you for your comments, Said. That's really kind. Oh, I'm glad you've, it sounds like a lot of people have enjoyed your talk this evening, Aslan, so that's really good to know. Thank you so much again for joining us, everybody. And just to let you know, this recording will be on YouTube, usually within about a week or so of tonight's talks. So keep your eyes open and look out for that. If you do need anything else, obviously do feel free to contact me, al@recworks.co.uk, or Barry or Helen, and we'll be able to put you in touch and get things answered for you if you've got any further questions. All right. Thank you so much for this evening. Have a great time.
Thank you, everyone, for joining.
Thank you. Thanks for coming. Thanks so much, Aslan. Take care. Have a good evening, everyone.